Welcome to this explainer. Before we even look at the agenda for today, I want you to try a quick thought experiment with me. Imagine taking a physical book, maybe your absolute favorite novel, packed with complex characters, specific words, and tons of information, and throwing it directly into the ultimate cosmic void, a black hole. So what actually happens to that book? Does the information inside it, the precise arrangement of the atoms, the ink on the pages, the actual quantum makeup of the paper itself, does all of that just get completely destroyed? Or does it secretly survive somehow, hidden away somewhere in the fabric of the universe? This deceptively simple question is actually the deepest, most fiercely debated unresolved mystery in modern theoretical physics. To really understand the stakes here, we have to look at the scene of the crime. Abraham Loeb, the chair of astronomy at Harvard, hit the nail on the head when he described the boundary of a black hole as the ultimate prison wall. One can get in, but you can never, ever get out. It is literally a one-way ticket.
Okay, let's dive into our roadmap for uncovering this 50-year mystery. First, the ultimate cosmic prison. Second, the unbreakable quantum rule. Third, Hawking's explosive paradox. Fourth, the black hole war. And finally, number 5, wormholes, hair, and holograms.
All right, kicking things off with Section 1, the ultimate cosmic prison. So according to Einstein's general relativity, the gravitational pull of a black hole is so intensely strong that it creates what we call an event horizon. This is basically an outer ring, a threshold, where the required escape velocity surpasses the speed of light. And since absolutely nothing can travel faster than the speed of light, nothing can escape this boundary once it crosses it. To anyone watching from the outside, your book has fallen in and it's just gone forever.
And right here is the absolute crux of our whole explainer. We're literally pitting the two fundamental pillars of modern physics against each other. On one side, general relativity is telling us the book falls past the event horizon and the information is totally lost. But on the flip side, quantum mechanics strictly forbids this. In the quantum world, information simply cannot be destroyed. No way, no how.
Which brings us to Section 2, the unbreakable quantum rule.
Okay, so it all comes down to the conservation of information. I know the von Neumann entropy math used to measure how much information we know about a quantum state looks a bit intense, but the takeaway is actually incredibly simple. Pure states must stay pure. If you have complete knowledge of a system beforehand, that information must mathematically exist forever.
This golden rule is called unitarity. It perfectly restricts how quantum systems evolve over time, guaranteeing that quantum information is never lost. Let's think back to our book for a second. If we know the book's exact quantum makeup before we toss it in, what physicists call a pure state, unitarity demands that this information cannot just vanish. It has to exist somewhere in the universe. Because, honestly, if the universe didn't preserve this information, the entire concept of cause and effect would essentially break down completely.
Moving right along to Section 3, Hawking's explosive paradox.
Enter the legendary Stephen Hawking. In the 1970s, he realized something wild. Empty space isn't actually empty at all. Thanks to quantum field theory, we know that particle-antiparticle pairs are constantly popping in and out of existence in a vacuum. And Hawking realized that these quantum fluctuations are happening right at the edge of the black hole's event horizon.
So picture this step-by-step process. First, these virtual particle pairs randomly appear right at the horizon. Next, one of those particles gets sucked right into the black hole. But crucially, the other particle manages to escape into space. The black hole actually has to pay the energy cost for this escaping particle, and over immense, mind-boggling periods of time, this continuous emission, which we now call Hawking radiation, causes the black hole to slowly lose mass, shrink, and eventually evaporate entirely. And boom, that triggers our ultimate paradox. See, Hawking calculated that this radiation is entirely thermal. It's totally random. It carries absolutely zero information about what originally fell into the black hole. So, if the black hole eventually disappears completely, leaving behind nothing but random scrambled thermal noise, where did the book's information go? If it's truly gone, unitarity is violated, and quantum mechanics as we know it is fundamentally broken. And let me tell you, physicists really don't like it when their rules break.
So let's look at the fallout in Section 4, the black hole war.
Looking at the timeline, you can really see how the tension escalated into a decades-long theoretical war. Back in 1976, Hawking firmly published that information is just lost, full stop. But by 1993, physicist Leonard Susskind formalized the paradox and pushed back hard.
Then in 2012, an entirely new theoretical bomb was dropped called the AMPS firewall. And it actually wasn't until the incredible breakthroughs of 2019 and 2020 that we finally saw a mathematical path to victory for quantum mechanics. Now that 2012 AMPS firewall proposal, it was pretty wild. Four physicists suggested that to save quantum mechanics, the event horizon couldn't just be a smooth, unnoticeable crossing. Instead, there had to be a firewall, a region of blindingly high-energy particles that instantly incinerates our book before it even crosses the threshold. The big problem here, this violently breaks Einstein's equivalence principle. Einstein said that free-falling into a black hole should feel exactly like floating in empty space, not like hitting a literal wall of fire. So actually, scratch that, we didn't solve anything, we just swapped one massive paradox for another.
Which brings us to our final act, Section 5, Wormholes, Hair, and Holograms.
To actually solve this giant puzzle, physicists had to radically rethink reality itself. It's fascinating. Holographic duality suggests our entire 3D universe might just be a projection, and the book's information is secretly encoded like a 2D hologram on the black hole's surface. Another wild theory, ER equals EPR, suggests escaping radiation is still connected to the inside of the black hole by microscopic quantum wormholes. And then there's the soft hair theory, which Hawking himself co-authored later in life, proposing that the event horizon isn't perfectly bald, but is actually covered in zero-energy photons that store all that data.
But the real major breakthrough finally arrived between 2019 and 2020. Using some incredibly complex math involving things called replica wormholes and quantum extremal surfaces, a new generation of physicists successfully proved that the radiation emitted by a black hole does eventually carry the information out. It follows something known as the unitary page curve. They proved mathematically that the outside radiation is highly entangled with the interior of the black hole. This was a massive, massive conceptual victory. Information is preserved. Quantum mechanics survives the black hole.
However, wait, before we pop the champagne and declare the case completely closed, there is a bit of a catch. You see, these groundbreaking calculations were done in idealized, mathematical toy universes. They act a bit like a simplified universe in a box. So, while the conceptual framework totally proves information can and does escape, the exact physical mechanism of how it happens in our actual, messy, real-world universe, that is still a frontier mystery of physics. Which leaves us with this final, incredibly profound thought to ponder today. To solve this black hole information paradox, physicists had to heavily rely on the holographic principle and quantum wormholes. So, if the universe has to encode information on 2D boundaries just to stop it from being destroyed by gravity, does that mean the rich 3D reality we experience every single day is essentially just a holographic projection? It is an absolutely mind-bending mystery that pushes the very boundaries of human knowledge. I really hope this explainer has left you eager to look a little deeper into the cosmos.